In this video, we will explore cross-entropy, a loss function widely used in neural network classification problems. In artificial intelligence, data can include not only numerical values, but also categorical data. Numerical data refers to continuous values, such as price and temperature, that can be measured on a scale. Categorical data, on the other hand, represents attributes like gender, color, or type. While categorical data can be encoded as numbers for processing by a computer, these numbers do not have inherent numerical meanings, such as greater than, less than, or equal to. When building an AI model, if the dependent variable y is numerical, the problem is typically considered a regression task. If y is categorical, the problem is treated as a classification task. As mentioned in the previous video on gradient descent, the mean squared error is calculated by squaring the difference between the actual and predicted values and then taking the average. The root mean squared error is also obtained by taking the square root of the MSE. Both the MSE and RMSE functions are convex and differentiable, allowing optimization algorithms like gradient descent to efficiently find the minimum value. Therefore, MSE and RMSE are commonly used as cost functions in regression problems, where the goal is to predict continuous values. However, they are not suitable for classification problems, where the output consists of categorical data. In such cases, a different loss function is required. Cross-entropy is a metric that measures the difference between two probability distributions. It is commonly used as a loss function in classification problems to evaluate the difference between the actual labels and the model's predicted probabilities. The cross-entropy between the actual label P and the predicted probability Q from the model is defined as the negative logarithm of the predicted probability for the correct class. In binary classification, where there are only two classes, 0 and 1, the cross-entropy loss function is expressed as follows. Y represents the actual label, which is either 0 or 1. Y hat represents the predicted probability of the model, which is a value between 0 and 1. Thus, log y hat represents the logarithm of the probability of the correct class, while logarithm of 1 minus y hat represents the logarithm of the probability of the incorrect class. If the actual label is 1, that is, y is equal to 1, the second term becomes 0, and the cross-entropy simplifies to minus logarithm of y hat. If the actual label is 0, that is, y is equal to 0, the first term becomes 0, and the cross-entropy simplifies to minus logarithm of 1 minus y hat. Let's take a closer look at cross-entropy using an example. First, when the actual label is 1, the cross-entropy is defined as the negative logarithm of y hat. This means that y hat represents the probability that the model assigns to the actual label being 1. When y hat is equal to 1, meaning the model predicts the actual label correctly with 100% certainty, the cross-entropy becomes 0. When y hat is 0 equal to 0, meaning the model makes a wrong prediction, the cross-entropy becomes minus logarithm of 0. As shown in the graph, the logarithm of 0 tends toward negative infinity, so the cross-entropy approaches positive infinity. Next, when the actual label is 0, the cross-entropy is defined as the negative logarithm of 1 minus y hat. When y hat is equal to 0, meaning the model predicts the actual label as 0 with 100% certainty, the cross-entropy becomes 0. When y hat is equal to 1, it means that the model predicts the label as 1 with 100% certainty, which is wrong. The cross-entropy becomes minus logarithm of 0, leading to positive infinity. Now, let's examine this graphically. First, when the actual label is 1, the cross entropy is minus logarithm of y hat. If y hat correctly predicts the actual label with 100% accuracy, the cross entropy approaches 0, reaching its minimum value. On the other hand, if the prediction is incorrect and y hat approaches 0, the cross entropy increases to infinity. Next, when the actual label is 0, if the prediction is accurate, the cross entropy approaches 0, reaching its minimum value. However, if the prediction is incorrect, the cross entropy increases to infinity. Based on this, let's summarize the cross entropy values for correct and incorrect predictions. In the case of a correct prediction, the cross entropy value is minimized, while in the case of an incorrect prediction, the value increases. In other words, as the model makes more accurate predictions, the loss value decreases, and as the model makes more incorrect predictions, the loss value increases. Furthermore, since cross-entropy is a differentiable function, it is well suited for gradient-based optimization methods. This allows the model to be effectively trained using algorithms like gradient descent. Thanks to these properties, cross-entropy is one of the most widely used loss functions in classification problems, and it is highly useful in both binary classification and multi-class classification. Let's apply cross-entropy to a binary classification problem. The task is to determine whether the given data represents a dog or a cat, with dogs labeled as 0 and cats labeled as 1. The model must choose one of the two classes for the input data, and the actual label for the given sample is a cat. After analyzing the input data, the model predicts the probability for each class. In this case, the model determines that the probability of the data, being a cat, is 80%, while the probability of it being a dog is 20%. By substituting these values into the defined cross-entropy formula, the cross-entropy value is calculated as negative logarithm of 0.8. Now, let's apply cross-entropy to a multi-class classification problem. Consider a scenario where we need to classify 3 classes: cat, dog, and rabbit. The actual label is a cat, and the model's predicted probabilities are 0.7 for cat, 0.2 for dog, and 0.1 for rabbit. By considering these values in the cross-entropy formula, the probabilities for the non-correct classes, dog and rabbit, are effectively ignored as they contribute 0 to the calculation, regardless of their predicted probabilities. In other words, the incorrect classes are disregarded in the cross-entropy calculation, and only the correct class is reflected. In the example showing 4 predictions, you can see that the non-correct ones all contribute 0, and only the correct one is considered in the cross-entropy calculation. If we were using mean squared error, we would have to compute the difference between the predicted values and the actual labels for all classes, resulting in higher computation and less efficient learning. Therefore, cross-entropy focuses on the correct class and reduces unnecessary calculations, making it more efficient and a better suited loss function for multi-class classification problems. All right, so to summarize, the cost functions used for regression and classification. For regression problems, cost functions like MSE, mean squared error, or RMSE, root mean squared error, are commonly used. For classification problems, cross-entropy is the standard choice. Specifically, binary cross-entropy is used for binary classification, while categorical cross-entropy is used for multi-class classification.